subspace, and V a vector in V. Then a best approximation of V by vectors in W is a vector W naught in W, such that norm of V minus W naught is less or equal to norm of V minus W for every W in W. We had also seen that if W naught is the best approximation, as we know that this is unique, then the inner product of V minus W naught and W is 0. That means V minus W naught and W are orthogonal. The best approximation W naught is unique. That also we know. And what it says is that V minus W naught is orthogonal to every W in W. So this is in the orthogonal complement of W. This is what. Now if you see this geometrically, we had seen already enough examples. And two things one can see is that if you look at the inequality that it shows, if you treat the norm of say U minus V as the distance between the vectors U and V. So the distance of the best approximation W naught of V from V is minimum from the distance of V with every vector in W. So this is minimum. So what you can see is that if you are having the case of say R2, in that case, say suppose V is R2 over R, and you have say one space say W, which is the line say y is equal to mx. Say this is the line y is equal to mx. So this W is basically here what you have W is. So it's x, and correspondingly you have mx. So x mx. For a fixed m, you can take m to be any real number. So x in R. You can see that this is a subspace of V. And so you can write that this is x, 1 and x. Say for example, when m is 1, then this is y is equal to x. And suppose V is any vector here, from here to here. So with the coordinates here, say 1, y1. Then the distance of this from every vector, yeah, this is minimum. So where is W naught that we had seen? This says that this is orthogonal. So this is the foot of the perpendicular. So this is your W naught. W naught is in W. So this is W naught. And these are the coordinates of V. So when you see that the distance here, if you take the distance of this from any other point, say some other, say W prime, then V minus W naught, this is this norm of this this norm of V minus W naught. And this is the norm of V minus W prime. And this is norm of V minus W prime. So this is always by the triangle, you can see, is greater or equal to norm of V minus W. So this is minimum. When does it become minimum? This is when this is orthogonal. And that's what is the second thing says, that V minus W naught is orthogonal to every W. Okay. Now, if you see, since W naught here in W is the foot of the perpendicular here, drawn from the coordinates of V, and this is the best approximation. So you can think that this is projection of and projection, which is orthogonal projection. So we therefore switch over to the projections, and particularly the orthogonal projection, not the inclined projection like this. So the orthogonal projection. So once again, let us take V over F be an inner product space over F, and in that case, so the vector W naught, and we denote this by say VE, is called orthogonal projection. We shall define what is this map E. So it is called orthogonal projection of V on W, where W is a subspace. W is a subspace of V. If every vector V in V has its best approximation orthogonal projection W naught, which is VE in W. So W naught becomes the orthogonal projection, as I just now said. If every vector in V has its best approximation, this vector W naught. So in that case, therefore, what we have this map, which is called the orthogonal projection of V. So this is from V to W. V going to the image is VE. This map is called orthogonal projection map or orthogonal projection of V on W. Hence, what we can see is that this E the map V to W, V sent to VE is an orthogonal projection of V onto W if and only if. So recall those things. So it clearly says that the norm of V minus W naught, norm of V minus W naught is less or equal to norm of V minus W for every V in V and for every W in W. And if W naught is the orthogonal projection, so this can also be written as norm of V minus VE is less or equal to norm of V minus W for every V in V and for every W in W. This comes from the first condition that this is also equivalent to. So this is equivalent to, you can see the inner product of V minus W naught and W is 0. That means what? That V minus W naught is an orthogonal complement. And that is same thing as V minus VE is in the orthogonal complement. V, you can say that VI, I is the identity map minus VE, which is same as V under the map I minus E. This is an orthogonal complement of W. So that's how you have the orthogonal projection E. And let us define now a map. So let us define the map, say E tilde, from V to this. This is, of course, a subspace of V that we know. In fact, we know that, and we have proved also in case of finite dimension, at least we have proved that V is the direct sum of W and W orthogonal. It's called the orthogonal complement. So V going to V under E tilde. So we are defining this as V the I minus E. So this that means this map E tilde is basically I minus E this map. So we know that V minus because of this V minus this VE. This is VE tilde. Now this V under I minus E is an orthogonal complement. That means what? This is V tilde. So this is V E tilde. This is an orthogonal complement. Now you can see that this V minus VE tilde. Yes. And here this any vector here you take to say for instance this W orthogonal in W orthogonal. This can be seen as V minus Now for V tilde, you can write that this is V minus VE, this, and W orthogonal, this, and this is V cancels with V. So this is VE and is W orthogonal. Now this is 0. Since this V under E is in W. The map is sending V to a vector in W. So this becomes 0. So what we have got here is that V minus VE tilde is orthogonal to every vector in the orthogonal complement. And that makes that this VE tilde is orthogonal projection of, so that makes the definition that we have here. So this tells that this V E tilde is an orthogonal projection of V onto W. So V E tilde is an orthogonal projection. So this E tilde is therefore is orthogonal projection of V on W orthogonal. And since that happens for every V, so this is what it is. Therefore, this map E tilde is orthogonal projection of V onto orthogonal projection. So what we have seen that if E is an orthogonal projection of V onto W, then E tilde is orthogonal projection of V on its orthogonal complement. You can also prove this alternatively if you want. So alternatively also you can prove what is VE tilde. So VE tilde, this is V minus VE. Now this is the best approximation, because of the inner product being 0. The best approximation of V by vectors in W orthogonal. Since VE tilde and the inner product this is same as V minus VE W, this is 0. And that makes that VE tilde, this is in the orthogonal complement of W. And that is since VE is the best approximation, as VE best approximation of V by vectors in W. Okay, because of the inner product of this being 0. Also, for every small w2 in this W orthogonal complement, norma for this V minus W is square is same as norm of, you can here write say adding and subtracting VE. So this is VE plus, so now subtract this, so V minus VE, add and subtract VE, minus orthogonal complement is square. And now this you can see is we have already done taking a product of this with itself. So this is if you take this VE as one, and another is this is another vector. So this is the norm of VE square plus square of the norm of V minus VE minus W orthogonal. Since what you see that V minus VE is the other terms will be 0, since V minus VE, which is V under E tilde, is in the orthogonal complement. So its inner product with every vector in W will be 0, and V is in W. W orthogonal is in W. So that makes that V minus VE tilde, and so that makes that V minus VE, which is same as V under E tilde. This is in W orthogonal. This is what it is. I have written it twice. I have written, so this is not required. This I have already written here. Okay. And this is this, and of course using this this is using a norm of x plus y square is norm x square plus norm y square plus the inner product xy plus the inner product yx. These two terms will be 0. That's what it is because of this happening. So this will be simply the square norm V square plus square of the norm of V minus VE minus W orthogonal. So what we have got is that norm of V minus orthogonal complement here of this W square. This square is same as norm VE square plus norm of V minus VE minus square. This is greater or equal to, naturally, norm is non-negative. So this is greater or equal to norm of V minus VE minus orthogonal square. Or if you take the square root, so makes that norm V minus greater or equal to norm V minus VE minus. Or that simply means V minus greater or equal to V minus VE. This is V under E tilde minus W square root we have taken from this. Okay. So this is the equivalent thing to say that VE tilde is orthogonal projection of V on, as this is happening for every W, orthogonal in W. So once again, we have proved the same thing, that if E is orthogonal projection then of V onto W, then E tilde is orthogonal projection of V onto W. So what we have got here is that if E is an orthogonal projection of V onto W, then E tilde, which is I minus E, is orthogonal projection of V onto W orthogonal. This is what we have proved. You can also prove that orthogonal projection is a homomorphism and its kernel is orthogonal. So further you can prove that the orthogonal projection E V to W this is V to VE, orthogonal projection of V onto W is a homomorphism. And its kernel is the orthogonal complement. And also that this is an idempotent, and what else? This. And using this, we can easily prove that V is the direct sum of W and complex. I wish to leave this for you because otherwise we shall not have much time for other things. Hope you will be able to do the proof here, but just to give you an outline. So for this, you can observe that W in W is the best approximation of itself by vectors in W. If the vector is in the subspace W itself, then the least distance from W will be 0. Now, V in V, for every V in V, VE the map, as you know, this is in W, and therefore VE under E, this will be VE. Because of this, that the best approximation, E gives the best approximation, this is the best approximation of this itself, and therefore this will be VE only. And that makes that E square is E, because this is for every E. That means this E is an idempotent. Okay. Also, this is what idempotent. Also, since V1 minus say V1E, this is always in orthogonal complement here, and V2 minus say V2E, this is this for every V1, V2 in. So that makes that V1 plus V2 their sum. That makes that their sum V1 plus V2 minus V1E minus V2E, which I can write as minus of V1E plus V2 of E. This being their sum is also in orthogonal complement of W. Now, what you can observe here, that this is an element in V, Vn plus V2. But this element here, this is in W, as the map is from V to W. So that makes that the inner product of V1 this with W, therefore should be 0. Because this whole linear combination of V1, V2, V1E, V2E is an orthogonal complement, and therefore this with W must be 0. So that gives me that the inner product of V1 plus V2 minus V1E plus V2E with W should be 0 for every W in W. And that makes that U minus say U naught W is 0. Where U is this and U naught is U is V1 plus V2 and U naught is V1E plus V2E. So this U naught is this makes that this is the best approximation. So this makes that U naught, which is V1E plus V2E, is the best approximation. यहाँ बाद में लगाना है. Of U is V1 plus V2 by vectors in W. So this gives us that this U naught, that is V1E plus V2E, is the best approximation of V1 plus V2, or V1 plus V2E. This is the best approximation. And similarly, you can also prove that for every alpha, in F, V minus VE in W orthogonal, we have this alpha V minus VE is in the orthogonal complement. This is in orthogonal complement. Every scalar multiple also will be the same. That is W orthogonal. And now that makes that its inner product with every. So this is alpha V minus alpha VE. This is in orthogonal complement. That means its inner product with every W is 0. And that makes that this alpha VE which is same as alpha VE. And that proves that E is a homomorph of V into W. So we had seen for this sum, and P is closed with respect to the scalar multiplication. So that proves that this is a homomorphism. This homomorphism is, by the way, onto. We map E V to W, which sends every V to VE, is onto. It's clearly onto. For WE, is W, for every WN. So you always have for every W, there is at least one vector. Namely W itself, which is the image of W under E. So this map is on. And what is the kernel? You can also prove next. The kernel of E is this. So for this, what you can prove is that let V be in V, then there exists a unique vector VE, the best approximation. VE in W such that inner product of V minus VE with the W is 0 for every W in W. That means that V minus VE is in the orthogonal complement. Now, this is in the orthogonal complement means that VE. Now, this belongs to W that we know. V minus VE is in the orthogonal complement, and VE is always in the V is in W, and V minus VE, this is in the orthogonal complement. And that makes that because of this, that V minus VE, this is in orthogonal complement, and this is 0. So VE is 0. So that makes that this is in the kernel. So this V becomes in the kernel of V. And that makes that orthogonal complement is contained in the kernel of V. So if you start V from the V lying in orthogonal complement, if V lies in there, then VE also lies in the orthogonal complement. So if VE lies in the orthogonal complement, V minus VE, this is always in the orthogonal complement. So that makes that this VE is in the intersection. And that will make that orthogonal complement is contained in the kernel. So if you begin with V in the kernel, we converse, begin with V in the kernel and show this is contained in the orthogonal complement. Conversely, kernel of E is contained in the orthogonal complement. For V in the kernel, this will mean that VE is 0. It is in the kernel, its image under E should be 0. And V minus VE, inner product with W, because this is best approximation, is 0 for every W in W. And that will make that V and W will be orthogonal. because VE is 0, so this is simply 0. And that makes this is here, V is in the orthogonal complement. And that makes that the kernel is contained in the orthogonal. So taking the two together, what we have got is that kernel of E basically orthogonal. And finally, so we have proved almost everything, so except that the direct sum. So let me do that also. So finally, V in V can be written as V as Vi. This can be written as add and subtract this E here. So V under E plus I minus E, which is same as that. And this is same as VE plus V under I minus E. E tilde. V E plus V under E. V is in W, and V E tilde, this is in orthogonal complement. So that proves that V is contained in W plus orthogonal. This is always contained in V. So that says that V is the sum of W and W orthogonal. An intersection that 0 of this, so that means that this is the direct sum here. Since W intersection W orthogonal is 0. So what we have got is this. Also we have proved V is the direct sum of W and W. So we have done the whole proof, although I wanted that we should do. As a corollary, you can prove here. So one corollary you can prove is that if E is orthogonal projection, of V onto this subspace W, then E tilde, which is I minus E, is an orthogonal projection of V onto W. And if this is an orthogonal projection, this is idempotent, then E tilde is also idempotent. Idempotent. That means E tilde, where is an E tilde. And is a homomorphism. Are there? E tilde is homomorphism of V onto W S with the kernel W. This is what I wanted to do as the projection. also almost over. Some people use the notation phi. Some use because this is because pi projection. Some people will use E for projection, orthogonal projection. E because this is an idempotent. So notation wise, some authors prefer to use pi, while others will use, for example, this. This is what is from my side. So since we are not left with any time, so we have to wind up here. And next time, then we shall move to some other topic. So thank you very much for your time and concentration.
Thank you, sir.